All right, so we're going to be continuing off from yesterday, and we were just at some unit conversions. I'm going to be doing an example right now of why it's important to sort of understand the process and being able to go from one system to another. And a lot of this is, maybe you'll have to look up something. Maybe you'll have to see, like in this example problem. Let me pull it up. Also, by the way, if you guys have a question or something and you put it in the chat, it's on a separate window, so I may not see it right away. There we go. Okay, so a car's driving at 90 kilometers per hour. How fast is it going in meters per second? And also, how fast is it going in miles per hour? This is something that's, is, I would say, a good introduction to converting some units because we have to do multiple operations. First, let's do the meters per second. So we'll start out with this car is going at 90 kilometers per hour. And you'll typically see these, a lot on like older cars. They'll have miles per hour gauge and also have a kilometers per hour gauge, sort of smaller within. But we have this car, it's going this speed. We can make sense of this by sort of breaking up the pieces and going step by step. So we'll break up this 90 kilometers per hour and we'll just make it look better to handle. So going 90 kilometers in 1 hour. So these two things are exactly the same. And that's what this is basically saying. It's going 90 kilometers in 1 hour. All right, but for this first question, we want to finally end up somewhere with a result that is in meters over seconds, meters per second. So we need to transform these kilometers into meters, and we need to transform the hour into seconds. So let's first, before I do that, let's put down some conversion rates that we know. So I'm going to put right here, I'm going to put conversion rates. Let's see. Okay. Conversion rates. Also, when I'm sharing my screen, I don't know if I have anyone in the waiting room still, so I might like pop out frequently to check. So we'll deal with that when it happens. Conversion rates, simple. We know that there are 1,000 meters in 1 kilometer. That's the prefix kilo is 1,000. So we know that there are 1,000 meters in 1 kilometer. What else do we know? Let me move this down again. What else we know? We know that 1 hour, it's just one unit. The unit is H. 1 hour is made of 60 minutes. And each minute is made of 60 seconds. So that would be 60 times 60. So I'm just going to simplify. I'm just going to put 1 hour. It's equal to 3,600 seconds, like that. All right, and the final one that's a bit obscure is there is 1.609 kilometers in 1 mile. That is one I would have had to look up myself. So we have these, conversion rates. What does one thing equal? There's someone waiting. Let me. Okay, awesome. So let's do this conversion. We have 90 kilometers in 1 hour. We need to go to meters per second. So let's, instead of having hours on the denominator, let's make that seconds. So we're going to multiply by this conversion rate right here. So in order to cancel out the unit of hours, we need to have hours on the top of this fraction over here. So 1 hour. So how many seconds are in 1 hour? And that's going to be this fraction that I'm making right now. So 1 hour is 3,600 seconds. Hopefully you could see I'm doing this just to put seconds on the denominator, because now I'm inserting this unit. You can see that the hours right here will cancel with the hours on the top up there. All right, so that is the reasoning behind, sort of the order, which one is on top, which one is on bottom. I'm doing this just because I want these to cancel. Okay, let me move that over. So I could, go step by step. I could then say this equals 90 kilometers over 3,600 seconds. And I can do the next step. And if you already feel comfortable with this, I can instead do all of the steps at once. And that's sort of what the book does. Let me just sort of show you the difference. And I'm sure this is, this is the beginning material. It's generally easier. But I want to show all the steps so everyone has a good base to start with. So if we did all of the steps at once, it would be multiplying by the next conversion rate. The next conversion rate is. So we have this 90 kilometers over seconds. So we have kilometers per second. We need to convert it to meters per second. So I'm going to be working on this one down here. The conversion rate I'm going to be using now is, first, what do I want to get? I want to have meters on the top, seconds on the bottom. So I need to cancel out kilometers. So I'm going to use this conversion rate up here and have 1 kilometer is how many meters? 1,000 meters. You see this conversion rate allows me to cancel out the unit of kilometers. This is on the denominator, that is on the numerator. So the units cancel out. And I would then just multiply 90 times 1,000. Then I would have an answer that is in meters per second. But just for the sake of doing this and the next little example, or any of your other work, you could do all of these steps in one. So looking at this top line, I could multiply by this conversion rate, and then I could also do 1,000 meters in 1 kilometer like that. And the answer ends up being, I believe, 25 meters per second, which, in the form I'm writing right here, it would be 25 meters in 1 second. And that is just written as 25 meters per second. All right. Now that we've done that, I'm going to get rid of this. I have a little bit of room. And we're going to do the next example and move on. So we have 90 kilometers per hour. I can write it more clearly like this. 90 kilometers in 1 hour. So what are the conversions I have to do here if I want to get miles per hour? So I want to end up with miles per hour. We already have hours on the bottom, so I only need to convert kilometers to miles. So what I have to do is multiply it by this conversion rate. I want the kilometers to cancel with something, so I need the kilometer value on the bottom. Like this. And I'm using this conversion rate right here. Since I put the kilometer value on the bottom, I'm allowed to cancel the units. And I'll leave that. And by doing this, I'm left with, I guess I could write it out full. It'd be 90 miles divided by 1.609. And the units down here are hours. And if you do this division, it turns out to be about 56 miles per hour. Okay, some basic conversions. It's good we got to see some steps that involved, multiple, we got to see an example with multiple steps. Next, we're going to go on to significant figures. Significant figures are, we'll be getting values that we need to, sometimes we'll be getting values that the calculator will just spit out. The calculator does not know when to stop giving the value. If it doesn't know how precise you want, so it's just going to give you everything. Sometimes you need more precision. You need to stay consistent with your operations. So we use significant figures. That is how many values in your measurements or your calculations that you can trust. And typically you're going to be using, let me see, typically you're going to be using the significant figures of this, or I'm sorry, you're going to be using the number that has the least significant figures. So I'll write out some examples and then I'll do a little clarification of what I mean. So we have this value right here. I'm just going to say 25. That has, let's count them. So it's 1, 2 significant figures. Pretty easy. 2 sig figs, usually what they're called. Then let's do 250. There is a problem here. We don't know if whoever took this value, it is quite large. Maybe they just rounding this last value right here. We're not sure if that 0 is, an accurate result, or if it's just someone saying, oh, it's about this many. That's why we typically don't count trailing zeros. Or let me just say no, and I'll clarify right next to it. So I'll say if there is no decimal point in this value, there is no decimal point, do not count trailing zeros. So what that means is this value right here only has 1, 2 significant figures. So that'd be 2. Sorry, let's go like that. By that logic, I'll do this next example that has this. If I do 250.0, okay, let's go right next to it. If there is a decimal point, you will count all trailing zeros, or I'll say all trailing zeros. Okay, so hopefully the logic behind this kind of makes sense. If I just write down on a piece of paper 250 without a decimal point, I'm not sure if someone rounded or not. Someone round up, someone round down. Why is there this 0 here? If someone writes this result on a paper, that means they are confident that this 0 is true, and they added that next 0, so that one is also true in their measurements or calculation or whatever they're doing. So in this case, we would have 1, 2, 3, 4 significant figures. Okay. Next example is, let's say instead of that, we'll do 205. Now this one will have 3. We're going to count all zeros that are in between non-zero values. So this will be 3 sig figs. Count zeros between numbers. Okay. And the last sort of example is we have some large things. What if we have something that's very small? What if we have 0.00250? Okay, so what is the rule here? I'm going to say for small values, you do not count the leading zeros. Okay, so that means all of these. I'm just going to say no. Then I'm going to say the same rule that applied up here. Since there is a decimal point, all trailing zeros do count. So in this case, we have 1, 2, 3 significant figures. Okay, and it's a little bonus. This is kind of what I was saying earlier. Let me make a little box area. If you're doing some kind of operation, you have two values that you're multiplying or adding together. You always let's write the example out. Say we have 200.0. In this case, that is 4 significant figures. And we multiply it by, I don't know, 3. That's just one significant figure. The result is going to be, what your calculator is going to give you. Actually, let's do it. It's like 3 points. No, we'll just say 3. That is just one significant figure. So the calculator is going to give you 6. Boop, boop, boop. Like that's how many significant figures should you trust on your result? Well, since we did this operation up here of 4 significant figures multiplying by a value of 1 significant figure, in this case, we're going to erase that last one, that last 0, and this will only have 1 significant figure. And that's what I mean by you always take the value that has the least number of significant figures in your result. That's so you don't sort of take values that the calculator gives you that might not be accurate. If you do this, you're sort of being consistent with your results. Okay, so I believe this is page 3 or so. Okay. There's that. And what's next? Next, we're going on to scientific notation. All right, so what is scientific notation? Well, in some cases, when you have your values, you're either measuring or doing some calculations. Calculator might spit out just this huge number, or maybe it'll spit out a very tiny number. And a lot of time it won't know how to handle it, so it'll just give it to you how it appears. In this case, maybe you will have a very large number. Let's go like that. Okay. We will have a very large number. 5, boop, 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 boop. And I don't know, decimal point is right here. We'll say this is someone measured it to be right here, and it's accurate. Now, scientific notation is a way for you to write this value down without having to put in all of these zeros over and over and over again. Maybe you're just carrying these through all of these steps, and it could be a real hassle. Let's that. So in order to get past it, where you have scientific notation, which will be, instead of writing this large number, we're going to write 7.5, and it's essentially me moving the decimal point a certain number of tens places. So I'm going to be moving it over 1, 2, 3, 4, 5, 6, 7. Okay, so I've moved the decimal place over 7 positions. So that's 7.5 times 10 to the 7th power. All right. And putting this in your calculator is a lot easier. A lot of scientific calculators have like a exponent function, or maybe they even have times 10, scientific notation function. In any case, this is easier to handle because it's only this value you're multiplying. And this one you can handle easier as well. So that's a large number. What if we have a small number? We have small number, just something arbitrary like this. Well, I'm going to move the decimal point over 1, 2, 3, 4, 5. I'm going to move it right there. So this becomes 6.0 times 10 to the, I moved it to the right. That's minus 5. And this one, I moved it to the left, so it's positive. That's just saying this is going to be, this is a large value, this is a small value. All right, some tricks about scientific notation is that we can multiply two values together and the exponents, the times 10 to the whatever. So that exponent we will just add. So for my example for this would be like we have 2 times 10. Let me hold on. 2.0 times 10 to the 4th power. And that's entire thing is multiplied by 3.0 times 10 to the 5th power. So in this case, I can multiply the values up front separately. It's going to be 6.0. And I will add the exponents. So this is 10 to the 4th. That's 10 to the 5th. I'm going to add these. So now we have 6 times 10 to the 9th power. It's much easier, and I could do it in my head without having to write 9 zeros down for the answer. All right, next up is division. Same basic thing. Instead of You're writing it all out, we can just subtract the exponent values. So let's say, I don't know, we have like 16 and 0 times 10 to the fourth power. And that's divided by 2.0 times 10 to the third power. So we would have a result of 8.0 times 10 to the, we're going to subtract the exponents, but it's just 10 to the first power. So I can leave it as just times 10. I can, make this times 10 to the first power. I could put 1, or for results, I could put, this is just 80. 8 times 10 is 80. So in any case, I'll just leave it like this so you can see the subtraction. Okay. And finally, addition and subtraction, just the very basic operations can be a little tricky because not all the time that the exponents are going to be the same value. So let's do that. Example, what do I mean? Say we have 8, or no, we'll make it like a 9, so we don't think it's connected to that. So 9 times 10 to the third power, that entire thing, and we're just adding 1 times 10 to the minus 2 power. That becomes something actually difficult we have to watch out for. So this value is actually 9,000. So I'm going to move the decimal over 1, 2, 3. So it's 9,000 plus 1. So that's 1, 2. So this actually equals and this is something that we can't express, cleanly. So we have to watch out for this if the exponents are not the same. We could keep the yeah, I'll just leave it like that. So next up, we have raising the exponent to another power. And that is simply just if we had something like this, I don't know, 3 times 10 to the third power, and we have to square the whole thing. Okay, so we have to square the whole thing. So 3 squared is 9, but the exponent is added times 10 to the 6th. I'm sorry, the exponents are multiplied. Okay. We're doing okay. Moving on to next section. Like that. Last look at that. Next section is on vectors. Okay. Vectors. What is a vector? Well, at this sort of pace, maybe in your math classes, you've already gone over these. This will be just kind of like a review. So we have ways to take measurements. We can take, measurements of something's physical properties. How big is it? How much time did that take? How much does this thing weigh? These are all values that are kind of like static. They don't change. Or they just have just sort of a unit by themselves, and that's meaningful. These are scalars. Go like this. Scalars are quantities that have a magnitude but do not have a direction. So the direction is not important or not connected to these values. And that's like, how much mass something has. Uh, this weight, this dumbbell has is 500 grams. That is just a value. Or this distance is 5 meters. Okay, these are just values that have a size. So magnitude is like, you think it's just the size, but no direction. And we have vectors. Vectors have a size, and they also have a very specific direction. So the direction is connected to the size. So they're sort of tied together. So quantities have both a magnitude and direction. Okay. So typically in pretty much all cases, a vector will be represented by an arrow. So you see an arrow on, a quiz or something, or your homework, it will represent a vector. This is a distance, and it's specifically going from here to there. It's got that orientation. Okay, so I believe what I was going to put like this for this example was, so something that just has a size. So think of like a length of a bar or something, metal bar. You could say that thing is 6 meters long. It's just a value it holds. That is a scalar quantity. Has a magnitude. Has a magnitude, but no connected direction. Then we have a vector, which is specifically drawn as an arrow. And this is something that maybe I'll say like, you need to walk 6 meters east. So that's me connecting a direction to this value. Okay. Out for this next one. Now, to represent a specific vector, let me move that up. To represent a specific vector, It's commonly just written as a term. It's given a label. It's vector A. That's vector B. The problems usually start with vector A because it's the beginning of the alphabet. But they could be labeled anything, but you'll know they're a vector because they have this arrow on top of the value, on top of the variable. If maybe you start with the vector, maybe they give you a vector and you want to find, for some reason, maybe you have the pieces for the vector and you want to find the size of it. It's unsure to you. The magnitude of vector A can be written as this. There's these absolute value signs around it. I'll go over how to find the magnitude in just a second. But by doing this, by finding just the magnitude, I'm sort of stripping away the direction connected to it. So it can be written as this or just A. So that's just the value of, this example. So instead of 6 meters east, it's just 6 meters. Okay. And I think the only thing I had for this was, on any sort of thing. They'll just be like a line, could be at an obscure angle, and it'll just be labeled like that. All right. Now that we have sort of an introduction into vectors, we can see how they're important and maybe add or subtract them. Let's look at the next page. Right about there. Okay. So vectors are very similar to scalars. You can add, subtract, multiply, divide. You could do pretty much anything with them, except you always have to consider that they have a direction sort of built into each separate vector. So you need to consider what sort of directions you are manipulating. Let's, for example, look at an object. Maybe this could be you in your car, and you have to drive to the grocery store. Okay, so we can look at the distance of you traveling to the grocery store, and you have to go down specific streets. Maybe you have to go around, and it's a long way to the grocery store. That can be the distance that you traveled. That's how much ground did you cover. That is a scalar quantity. It's just a value. Think of the ticker on your car, the odometer. It counts how many miles you've gone over. That's a scalar quantity. It's just a number seeing the distance that you've traveled. But what if we want to look at a vector of you traveling to the grocery store? We could do all of the individual streets, or we could find what is called the displacement, which is a vector quantity. So displacement vector. also what it's called sometimes. So let's see, I need to go like that. Okay, so let's say we start at point A. I don't think you need that top bit anymore. We'll go like this. So vector A, sorry, you're starting at point A and you're going to point B. The path directly there is the displacement vector. So distance, you think of it as just like total amount traveled. And that's why it's a scalar quantity. Displacement, think of it as the difference between where you start and stop. Okay, so if this straight line right here is the displacement, let me, let's back up to that grocery store example. So start at point A and you have to drive a long way to get to the grocery store. And this is going to be this dotted line. So you go down some streets, around some hills, over here, and you finally end up at the grocery store. Just some very obscure path. It doesn't matter quite how you get there. It's just a distance that you've traveled to get there. The displacement in this example is if I took a picture of you starting at point A, and then I took a picture of you again, where do you end up? We end up at point B. So that is this displacement, which is this solid blue line. That's the difference from where you start and stop. It doesn't really matter the path that you exactly took. And that's why this is a vector. Okay. I might have to move that. Okay, let's see. Okay. Yeah, I made it too big. So okay. So adding vectors, maybe we want to add multiple vectors together. How can we do that? We can do it, on paper with, just the math portion of it. We can also typically do it with, a picture graphically. So I'm not saying it's all of the time. Sometimes you could encounter something that's like it's representing an arrow, a vector, but someone just doesn't draw it to scale. So I'm just going to say most of the time you can do it graphically. If you're doing something yourself, you can always draw something to scale if you have like a ruler and maybe a protractor. But let's say we want to add a few vectors together. We can do graphically, just drawing this out, we can do the head to tail method. And there's also an equivalent method. It's just called the, I believe, parallelogram or tail to tail method. So let's go like this. So let me try to draw these. I'm sorry, let me go like that. So we want to add two vectors together. Let's say there's vector A, which goes like that. And then there's vector, or let me label it A. Then there's vector, try to make it a straight line. I'll just go like this. Cheat a bit. Vector B. Okay. We want to add these two together. This is the head to tail method. Head to tail method. And we can see that I start here at the end, or the beginning of point A, and I end up over here, the very last part of point B. So by adding these two things together, I can find the total displacement, which is just this. I've labeled it up above. It's the resultant vector. And that is this vector that connects the two. Let's try to make this a straight line. Like that. Let me, one more time. Like that. And this resultant vector I can call vector C, like this. I could draw it as a solid line. I believe in some examples I might make this a dotted line. But this is the result of adding vector A and vector B. So I could put down vector C equals vector A plus vector B. All right. The next method was the tail-to-tail or parallelogram method. Let's try to draw these angles again. So A, it's pretty good. So there's vector A again. I'm trying to make this the same as this first example. So there's vector A again. And here's vector B. I'm going to start the same point. So tail of the arrow and tail of the arrow. I think that needs to be a little longer like that. There we go. This is vector B. Okay, so why it's called the parallelogram or tail-to-tail method is I can then take this section and I can map it up here to the top. I'm just going to go like this and I'll make it a dotted line in a minute. Vector B, and here is vector A again. I'm going to make it a dotted line. And we see that by having these two here, I could maybe make this weird parallelogram. And the very opposite point, that is where that resultant vector is going to end up. So it's going to start at the tail to tail again, all the way over there. That is the resultant vector C. C equals vector A plus vector B. parallelogram, parallel, or tail to tail method. Okay, I'll I'll make that more readable after class when I clean these up. Okay, so we have this way of sort of positioning these vectors. The vector is always going to be pointing in that specific direction. We have these ways of sort of adding them together and finding the resultant vector. How do we find these, values? I could say vector A plus vector B equals vector C, but if I'm given a list of values, how do I actually, do the math? How do I calculate this thing? So let's pull that up on the next page. Okay, so we have to look at vector components. So what is a vector made out of? So every vector that we're going to be dealing with, that we're given, can be broken up into pieces. These pieces are, a lot more manageable than the vector itself. I can say vector A plus vector B equals vector C. That is actually a little complicated. I need to find the components first. So let's make some components for a vector, or let's demonstrate. So we have this Cartesian grid here. That. So we have this Cartesian grid here. And let's say there's a vector that starts at the origin. Now I could make a vector out in space somewhere, but then I could just move the origin to where it starts. So I'm going to say the vector goes like this. And that's pretty good. I don't want to zoom in too much. So, okay. So we have this vector. It is called vector A. Now, vector A, I've added this, Cartesian grid. I've added this sort of reference frame. It starts at 0, and I'll be able to actually have some measurements. So vector A is this, it's specifically this long, and it's specifically pointing in that direction. So that means we can sort of measure this angle from the x-axis up to the angle itself, or the vector itself. And that is going to be angle theta. That is this Greek symbol right here. Sort of looks like a 0 with a line through it. We can find the angle of vector A. We could also, let me introduce some of these ways to break up this vector. So I'm going to be putting some dotted lines down. That's it's going to be dotted line. And that is also a dotted line. Okay. So the reason I added these dotted lines is because if you look down at the bottom here, this is a 90-degree angle, the dotted line that I made, and this x-axis. Right there is a 90-degree angle. 90-degree angle means that this interior, just gonna scribble real quick, this interior makes a triangle that I can actually solve a lot of very easily. I can also see that by breaking up into these sort of triangular chunks, I can maybe notice if I make it sort of a tick mark right here, that vector A, this random line, has a width of the triangle that is this big. It has a base that is that big. So I'm going to call that A sub x. So this is just a small value representing what axis it's on, or what side of the axis it's on. So that is specifically just this length right here. And that is a scalar value. So what is the base of this triangle? That's A sub x. I can also look at the height of this triangle. And that's why I made this other dotted line up here. Its tick mark goes right here. And if we're starting at the origin, which is 0, I can count all the way up to find out how tall this triangle is. That is A sub y. That is the height of the triangle. I could put this here, or I could put it over here. Same thing, A sub y is the height of the triangle. I'm going to leave, I'm going to leave A sub y over here. Just know that I could put this on either side, left or right, because it's the same height. Now, maybe I want to actually find these values. I want to find A sub x. I want to find A sub y. How can I do that using what I'm given? Well, maybe I'm given the angle in the problem. And maybe I'm given, maybe I'm given the vector and its angle, and I need to find its components. That's the problem it's asking you to do. So I can refer back to some trigonometry. I'm going to put up here SOHCAHTOA. SOHCAHTOA. Now, if you weren't taught this in geometry or trigonometry, what this is that for a triangle, we can look at the angle of the triangle that we're solving for. We say that sine of the angle is the opposite length over the hypotenuse length. You go like that. Next up, we have, I'll just write it real quick. Sine of the angle is opposite over hypotenuse. This next one is cosine is the adjacent side over hypotenuse. Adjacent, so I'm just going to put ADJ. I'm running out of time for today. Over hypotenuse. And this t is tangent of the angle is equal to the opposite side over the adjacent side. Now, so I will make this a bit, I'm doing this quickly. So if we want to find specifically this length, let's say a sub x, we know this angle, we can use, maybe we can use cosine of the angle equals a sub x. So cosine is adjacent over hypotenuse. So that would be a sub x over, and in this case, it would just be the value of the hypotenuse, the magnitude. So that's why I'm not putting an arrow. So that's why I can say that a sub x is equal to the magnitude, just the size of the vector, times cosine of the angle. Okay, let me move that up. Run out of room. Next up, with this orientation, I could say maybe to find the a sub y, using the same logic, use sine of the angle is a sub y, that's opposite over hypotenuse. Y over a, that is a sine theta, like that. Okay, I'm gonna shrink this down because it's in the way a bit. Okay, and I'm gonna move these up. Now, how do we find the angle? Maybe we're not given the angle theta. So we could find theta with, we could use any of these. We can also use tangent. That's the only one I haven't used yet. So that would just be tangent of the angle is a sub y over a sub x. And that becomes just an inverse tangent of a sub y over a sub x. And that's how I can get the angle by itself. To find that. And lastly, maybe I need to find the size. Maybe I need to find the magnitude of this vector. We could find magnitude. Magnitude A, so that's without the vector sign. And that is just by using Pythagorean theorem. You remember what that is? That was, so this is a triangle. And if we want to find the length of the hypotenuse, it is, this would be a, you know, the formula is a squared plus b squared equals c squared. So in this specific example, we have a, magnitude a squared equals ax squared plus ay squared, which just becomes this. All right. And that is a method to find the magnitude. Which room I overdid it. Yeah. So let me shrink this just a hair. Okay. The last little bit for today is, now that we have these components, we have, a way to find the, x components of a vector. We can find the y component of a vector. Now, what if we have more than one vector though? We have maybe two. We can start handling multiple vectors. So this is where, that previous example, vector A and vector B, adding vector A to vector B equals vector C. So let me do that example down here. And I'll try to make it large. So we can see. So it was, vector A like this. And it was vector B. I'm just sort of making it more dramatic. Actually, I can't make it a flat line. So it's going to be slightly different. There's vector B. And vector C is the resultant. So it's going to be the one that goes from here all the way up here as vector C. How can we actually figure out any of these values? Well, we just take it piece by piece. So vector C, we know that vector C is made of adding vector A and vector B. A plus vector B. We also know, make this a little closer. We also know that vector A is made of X and Y components. So I'm just going to very quickly, this is a dotted line that I'll make. And that's a dotted line. So vector A is made of its Y component and its X component. And vector B is also made of its Y component and its X components. And so hopefully with these sort of steps that you can see that if I add A sub X and B sub X, I will get this large resultant component down here that is called C sub X. Then if I add these vertical bits, I will get a large Y component. Go like this. That is called C sub Y. Move this over, just a bit more room. So with this, I can see that C sub X, this large one on the bottom, is made of adding, C sub X is made from adding A sub X plus B sub X. And then I can also see C sub Y is made from adding a sub y and b sub y. And with this, I have these two large components. With these two, I can then find vector c by using Pythagorean theorem, like I showed before. All right, it's 2 minutes over, but I believe I'm in a good spot for tomorrow. I'll start the next chapter. This is pretty much all of chapter 1. Yeah, other than that, if you guys have questions, you could ask right now. If not, I will see you guys later. And then I will be posting the video and the notes probably in an hour or so.